All right, welcome back. Another short video today. And once again, we're talking about streams. Let's start out first with this short little applet. Let's hope it's working. This just shows the movement of different materials on a stream bottom. And you can see in the bottom part, there's large objects rolling, sliding, bouncing, hopping. Let's start it again. In the middle, you'll see material that's suspended by the turbulent nature of the water. And those suspended particles happen to be small enough to be held up by it. Now another label there says dissolved load. Dissolved load are the things that are able to be dissolved by water, like salts. And they're not actually visible. They're invisible at this point, dissolved in the water. But they're still in it. They're moving along. And perhaps up at the top, there might be some organic matter, some leaf matter, and those things might be actually light enough to float. So streams can move things in a number of different ways. By bouncing and sliding along the bottom, they call that saltation, by suspension, by dissolved load, and by flotation. All right, so let's get these down. Solution, dissolved material, including salts. Suspension, these are the particles that are small enough to be carried in the turbulent flow of the water. Clays, silts, and sands, definitely the clays. And the bigger stuff bounces and slides and rolls on the bottom. And those are like the pebbles, cobbles, and during flood events, perhaps boulders. Now, as streams speed up, as their velocity increases, the larger the amount of particles it can carry. So it can carry more sediment and larger sediments. And you've noticed this after floods, the rivers around here turn dark brown. And that's just the sediment load has increased drastically. All right, now this chart is in your reference tables. It's on page 6 in the upper right. And what this chart represents is the relationship of transported particle size to water velocity. And over in the blue box here, you can actually see water velocity determines the size of particles that can be moved via suspension and bed load. So we got some questions here. First question says, how fast does a stream have to flow to move the largest sand? So let's take a look at how this chart works. First off, we have particle size, which is the diameter of the particle on the y-axis, and it's broken up in increments, multiples of 10, and a logarithmic type scale here. And on the other side of the y-axis, we're used to this from the sedimentary rock lessons we've had in the past, where it breaks up the different particles by name. Now on the x-axis, we have stream velocity. It's measured in centimeters per second. And once again, you can see it increases in a different amount you're used to. Each major line over is 10 times bigger than the line before it, which is another logarithmic nature. All right, so let's answer our question about the largest sand. So we look over here at sand, and there's the smallest sand at 0.006. And we have our largest sand at 0.2 centimeters. And so we need to find out how fast a stream has to move the largest sand. We simply go there, we go down, and we see it's about 10 centimeters per second. So 10 centimeters per second. A 1 centimeter pebble. All right, now the right-hand side isn't as useful for that, but the left-hand side definitely shows a 1 centimeter pebble. And so we're just going to follow that line over and follow it down as best we can. And it looks like not quite 50, maybe 55 to 60 centimeters per second. All right, number 3, the smallest boulder. So boulder has no upper limit on this chart, but the smallest boulder is right there. And if we follow the chart down, straight as we can, you might want to use a ruler for this, a straight edge, comes out to about there. And that is yes, 200. There's 100, 200, 300, 400, and 500. So 200 centimeters per second. The last one, the largest clay. Now clay has no lower limit on this chart. We can definitely see its upper limit is 0.0004. So we follow that over till we hit the graph. When we go down, looks like that line right there, which would be not 0.001, but 0.02. So 0.02 centimeters per second. And that's essentially how you use this chart. You can either work from stream velocity to size or size to stream velocity. All right, hope this made some sense.